In data structures and algorithms, you were given a computational problem, often a puzzle problem, and you have to solve it by designing a correct and efficient algorithm. That's the problem solving part. And then you have to code up the efficient algorithm you designed. That's the second part of a coding interview. And the assumption there implicitly is that your program or function that you wrote is being called by some user, presumably the interviewer who's sitting um, or standing next to you, with specific test cases. Those are going to be the parameters to your functions, and you generate a specific output. Your program runs on those test cases, and if it returns the specific expected output, uh, you pass the interview, and your program also comes to a halt, and things just finish there. And your program uses the processor CPU of a single machine. It's running on a single machine and running on a single processor on that single machine. And it has a theoretically unbounded amount of RAM to run on. So all the inputs to your program, all the data structures you write or implement, they're all lying in main memory. And if your program runs correctly, the efficiency of your program or your algorithm, the running time, is captured by asymptotic analysis. So the amount of CPU you used is quantified as the asymptotic time complexity of your uh, algorithm. And the amount of space that your program used is quantified as the space complexity. And both the time and space complexity are a function of input size. In reality, we know they are system dependent, they depend on a lot of system specific things, but in coding interviews, we assume that the only variable that they depend on is the input size, which is often parameterized as n. And because RAM is unbounded, you literally assume that n can get arbitrarily large, and you look at what the rate of growth of the running time or space usage is. For example, if you're given the sorting problem, then assuming a single machine, a single processor on that single machine, data in RAM, an algorithm like merge sort takes order n log n time using order n extra auxiliary space. That's something you're used to. When we move to systems design, if you want to have a smooth transition from algorithms to systems design, you should start thinking of your standalone program as now an online service. And that means the users of your program are not that single interviewer. They are actually clients who are residing very far away from you, potentially on the other side of the world. They might want to execute your program remotely over the network. And so they send in those inputs in the form of a network request. So they send this request across the network to your machine, which is running the program, and we'll call that the server machine, which will run the program on the inputs that they sent. And they specifically are interested in the outputs. So when your program creates the output, we return the output back to them as a response again over the network. And because there are many users, many clients around the world sending in these requests all the time, your server is always on. There is never a point where you say, I'm done, and your program halts. You might finish serving a single request, but these requests will keep coming in from several users. And what you want to do is first build an online service in a way that's also scalable, which means when the traffic increases, when the number of users and the number of simultaneous requests they're sending in, as that number goes up, you want to still be able to serve those requests without sacrificing the response time. And that's what we call as a scalable service or a scalable system. And in systems design interviews, you will commonly be asked to build such an online service because most of the companies you will be interviewing at will be having some online service as their main product. And so um, this is where your data structures and algorithms knowledge is combined with real systems knowledge to see how or if you can actually design a system in the real world. Now, an online service system of the kind I described can be visualized as a black box. Um, so there is a client, as I said, or a bunch of clients. They send in their request into this black box and they get back a response. And what they see is just the interface. They don't see the internal implementation of this system. And internally, you could have a bunch of components or subsystems which interact with each other to provide and expose an overall functionality at the interface, at this green interface, which is what the clients see. And each of these components inside can be large in themselves. And in fact, they may not even be located at a single place. They can be so large that they might have to be geographically distributed. So we define a system in this way. It's a collection of subsystems or components which interact with each other to provide this overall service at the interface to these end users, to these clients. But this is a recursive definition. So if you zoom into any of these smaller boxes, they in turn would be composed of smaller and smaller components that interact with each other to provide some kind of uh, interface, some kind of service to other systems on which are interacting with them internally here inside this overall box. But if you keep zooming in, at some point your recursive definition will end up at some base cases. So at the smallest level, we don't have to go to the subatomic or even the transistor level. We stop at the point where we reach atomic units, which could be processor, CPUs, they could be memory units like RAM or disk, and they could be communication links. They could be, long optical fiber channels across, the Atlantic or the Pacific, or they could be, small buses that are going from a processor to memory somewhere locally. So at the most fundamental level, any system, any computer system and any scalable system is composed of compute, memory, and network resources. And so you have to build this online service out of uh, these fundamental atomic units. Now, similar to data structures and algorithms in coding interviews, it is expected that you will design a system that functions correctly. So you have to return a correct response, which is expected by the clients. And when it comes to the performance evaluation of your system, we don't use asymptotic time or space complexity. We use other metrics. And the most fundamental of those, there are actually three of them. The first is the response time. So when we think of the response time from a client perspective, it is the time that it takes the request to travel from the client to your server, the time it takes for that request to be served by the server, the service time on the server, and then the time it takes for the response to come back. So we can write the response time as the sum of the network delay in both directions, right? The round trip network delay, which is what we call as the latency, plus the time it took for that request to be served on the server. So let's call that the service time on the server. And this is something we want to minimize for our clients. The response time should be as low as possible, ideally within a few hundred milliseconds. Large companies like Google and Amazon have found that when you increase the response time for the clients beyond a few hundred milliseconds, then for every incremental um, increase in the delay by even 100 milliseconds or so, there is a noticeable drop in the ad revenues or in the sales. And so it's important to keep the response time within a few hundred milliseconds. We also want the service to not have any downtime. So roughly a service is available if it's always up. If you want to quantify it in a more mathematical way or in a more measurable way, you could pick a measurement window, say a month, and over the course of 1 month measure what fraction of valid client requests got back a response. And that fraction is what we call as availability. So we want the availability to be as close to 1 as possible or 100% as possible. That may not always be achievable. So we at least want it to be something like 99.999 or 99.999. Of course, it depends on your system, but in general, high availability means something uh, of the order of 99.9, 99.999, and so on. So we count the number of nines and we say availability should be, let's say, 5 nines. When we say availability should be 5 nines, we means should be 99.999 because that has 5 nines. So availability should be high in general. We also want the system to be able to handle all the client traffic. So as the load on the system grows, we want to be able to not drop uh, these client requests. We want to scale our system. So in terms of the number of queries per second that the system can handle, which is what throughput is, we want the throughput to be high. Now, how high? Well, we can't put uh, a numerical value to this because this really depends on how what the traffic is. So this is not something in your control. You just have to ensure that uh, you're not dropping a significant amount of traffic. And as you can see, these are related. If you can't handle all the traffic, then your availability will drop. And if you're having a hard time serving all the requests, then maybe the response time seen by the clients will also go up because the service time on your server might also increase. So they're not independent metrics, they're related, but we try to simultaneously keep response time low, availability high, and throughput also high. Now, in order to understand how to build this kind of online service, we need to go beyond our knowledge of data structures and algorithms. Our data size when it comes to large scale systems is going to be huge, big data as they call it. And so it's going to commonly reside on disk, not just RAM, unlike data structures and algorithms. And so some knowledge of database systems is going to be essential. Since these clients that you're serving are geographically dispersed and will be sending requests and receiving responses across the network, some knowledge of computer networks is also useful. And since in general, your server machine is going to have multiple copies of your program or your function running, not just a single copy, those multiple copies will be competing for access to the same CPU or memory or network resources on that server. And so managing access to CPU, memory, and network resources on the server is something that operating systems manage, is something that operating systems do. And so some knowledge of operating systems is also required. And finally, since in order to scale, what you will do is not to make the same machine more powerful. You will follow what large companies like Google, Amazon, and others do, which is to use commodity machines and to use a large number of them and coordinate uh, interaction between them so that overall they work together to provide the online service to the clients. And so we'll in general have several independent machines communicating with each other across the network. And so knowledge of distributed systems is also going to be useful. So as you can see, there are at least 4 different fields that you need to be aware of, bringing together knowledge from all 4 of them in order to uh, build large scale systems. Now, an online service system, which is large in itself, think of a Google, Google search engine, for example, will often have an offline subsystem within it, right? So if you go back to that picture of a system with uh, an interface exposed outside and being composed of a collection of subsystems, one of these subsystems or some of these subsystems might not be online, they might be offline. And what we mean by that is the if when you peer inside that box, you might see that the input to the program that is running there might be a large huge file, right, which has been generated across a period of time, maybe a day, maybe a month, and your program runs on that input and it generates a large output file, and that output file is also loaded periodically into uh, some other part of your system which is client facing. So basically this red box that I'm talking about, this component, might not be online. It's run periodically as an offline system, and we call this a batch processing job. So it might run periodically, say once a day. Uh, to give an example, when you look at a search engine like Google, uh, when the query comes in from the user, you have to return the response back quickly. So it's clearly an online service. But within a search engine, in order to serve the user query, there might be a data structure that you use. And that data structure could be huge in size. It might not even fit into one or even a few machines. You might need hundreds or thousands of machines to store it. How do you build that kind of structure? One way in which you could build it is by building it as part of a batch processing subsystem. And so it gets built periodically and then loaded into some kind of um, user facing component within that system. So when a new version of it is created, it could replace an older existing version. That's how Google replaced their search index in their early years. They would run a batch processing job once a month, which would create that data structure out of all the pages that had been crawled over that month, and then replace the old index with a new index. But over time, many of the batch processing systems changed in that there was a need to update the output file or whatever the output is much more frequently, right? So, and that led to a transition where we didn't wait for a large input file to be built and accumulated as in a batch processing uh, job. Instead, we imagined the input to be constantly changing, to be coming in, new input coming in all the time, new pages that are being crawled coming in all the time. And that's what we call a data stream. It doesn't have a fixed size, it just keeps coming in. And there is some producer who's producing that input in that stream. In the context of a search engine, it could be a crawler that's constantly crawling and feeding in new pages. And your program needs to almost continuously consume that input and keep updating that new output in near real time, right? It doesn't have to be done exactly in real time, but you don't want the index to be stale for a month. Maybe you want it to be stale for only a few hours or maybe a day or maybe a few minutes, or maybe as soon as the page is scrolled within 1 minute, you want uh, the data structure you have to be changed so that the users see the updated version as quickly as possible. So that's what stream processing subsystems are. They work within an overall online service to provide uh, uh, output which is updated a lot more frequently than batch processing systems. So when we study how to design large scale systems, we divide our study into 3 units. The overall system is typically an online processing system. It's providing an online service, but within that online service, there could be subsystems, which could be batch processing systems or stream processing systems. And in this talk or this presentation, we will look at how to design an online service with a batch processing component. If I just covered batch processing in isolation, that may not make much sense because batch processing systems don't work in isolation. So we'll try to see how we could design a search engine from first principles. That's the goal. Now, in a systems design interview, the way you would be asked to design the system is by means of a very brief problem statement. For example, it could be design a search engine, right? It could be a generic search engine for product search, could be Twitter search, any kind of search engine in any context. Uh, we'll think of a search engine like Google for the purpose of this presentation. So what your job is to unpack that problem statement into a more elaborate problem statement. And that is usually the first thing you do, which is to come up with a more detailed set of functional requirements. These are more detailed problem statements in plain English, which just describe the in a non-technical way the user's view of the system. So, for example, we all know what search engines um, look like, how users interact with them. They essentially submit queries. So, when you think of a client as sending a request to your system, it's essentially a query, and the response expected back by the client is a list of relevant document links, right? A page, search results page with a list of relevant uh, document links, which you can click on if you find any of them to be relevant or satisfying your information need. So the purpose of this initial part of the interview, lasting around 3 to 5 minutes, is to also show the interviewer that you can communicate and unpack the short open-ended problem into a more elaborate and specific set of requirements. So you keep asking clarifying questions about whether the interviewer wants you to implement this specific feature or that specific feature, visualizing yourself as a user interacting with the system. And when you're gathering functional requirements, you shouldn't get too distracted by the scalability requirements, because until you have a functioning system, there is no point in even thinking about scaling it up. So scalability requirements or non-functional requirements or capacity requirements, as they're called, might be given by the interviewer anyway, but in your mind, you can set them aside temporarily and come back to them when it's time to scale. So in our case, the functional requirements that we are working with are pretty uh, clear, and we'll actually make them even more specific to start with. We will say that our query that the user will submit to the search engine is going to be a Boolean query. And what is a Boolean query? It's just a bunch of words that are connected together by Boolean operators like and, or, and not. So for example, an AND query like this would ask for all the documents in your system which contain the words Brutus and the word Caesar, both of those words. An OR query would ask for documents which contain either the word Caesar or the word Cleopatra, and a NOT query would ask for documents which don't contain this particular word, right? So you can imagine the user submitting um, a simple Boolean expression like this, or it could be a much more complex and long Boolean expression. And for now, to start with, we will change this assumption later, but for now, let's assume that the documents we are talking about in our search system are just the 37 plays of Shakespeare. This is useful when you have no clue how to design a large scale system. You first think of designing a small system and then scaling it up. So on the plays of Shakespeare, we want to build a Boolean uh, retrieval search system. Now, the next step in a systems design interview, once you have the functional requirements, in our case, it's just just a single functional requirement. Typically, you might have lots of requirements, right? Maybe 5 or 6 or something like that. So in that case, you would, in your second step, put on the hat of a VP of engineering or a director of engineering at a company that is asked to design this system and cluster these functional requirements into a collection of microservices. So think of dividing up your work into across a bunch of teams. So ask yourself whether you would hire a single team to implement that system or would you hire multiple teams. And the rule of thumb is that if, in order to implement two functional requirements, you find out that both of them are going to rely on completely different pieces of data, both of them will need to access two completely different data structures, the inputs and outputs in both of those cases look quite different, then it makes sense to put them into two different buckets. And just to give an simple example here, if we also had a functional requirement saying that for a user to use my search engine, the user should be logged in, there should be an account created and the user should be logged in. I'm not going to allow um, random visitors to use my search engine. Well, in that case, you would also have to implement authentication, account creation, login, and so on. So the team, informally speaking, the team that implements authentication would be different from the team that's actually implementing the core search service, because for implementing account creation, login, and all that, you're going to be maintaining the user information in a completely different data structure or a different um, database. think of a data structure if you have a difficulty directly thinking about databases. It's clear that the data structures are different, and so even though there is some subjectivity to it, if you use these simple heuristics, you might be able to come up with a collection of microservices at the end of step two, right? You would know at the end of step two whether I have only a single microservice to implement, or whether I have a bunch of microservices, a bunch of teams, each of which will be implementing one piece of the overall system. And that tells you whether the systems design problem is a depth oriented problem or a breadth oriented problem. In our case, we are going to skip this step because, well, we're not exactly skipping. We just said that we have a single functional requirement. So there is only one type of request. And so we will pretend that we have only a single microservice to implement, and we are going to go deep into this problem. If it was a breadth oriented problem where we have to implement login and reviews and all those things, then or payment processing and so on, then we would have a bunch of microservices and we would have to divide up the time in the systems design interview across all of them. So budgeting of time would become a lot more important there. And step three is what you would do if you had multiple microservices. If you had multiple microservices, then the first thing that you would do is draw a rectangle for each of them and then show how these different microservices interact with each other to provide that overall functionality that we talked about for the client um, who is going to be sending the queries to you, to your system, right? So maybe authentication, maybe this microservice implements authentication, this microservice implements search. So then you would need some kind of logical architecture diagram connecting these two. So you would have some kind of gateway which will take the client request, first check if the client is authorized or not, and then send the request down to the core service to get the response back and send the response to the client. So some simple, high level diagram like that showing how the logic and the data would flow across these multiple microservices. So we are going to skip this step two because we have only a single microservice to implement, and so all our time is going to go into that. And so recall the three steps: gather the functional requirements, cluster them into microservices, and if there are multiple of them, then first draw a logical high level diagram of connecting those microservices. We don't have to deal with step three, we just move to step four. So in step four, you will, for each microservice that you had in your logical architecture diagram, you would do a deep dive into each of them. You would open the box and explain how you would implement each of them. In our case, there's only a single microservice. But if there were many, you would have to budget your time, negotiate with the interviewer to figure out which of them is the most important or crucial to focus on. And remember that if there is only one microservice, as we have in this case, there might be a coding part to the interview. And that is why simple system design questions like URL shortener, for example, continues to be asked, because in the URL shortener system, there is also coding part to the interview. So the same interview can test both your coding or problem solving skills and design skills. So for the rest of this session, we are going to be doing a deep dive into the search microservice. Now, how do we do a deep dive? How do we implement any online service or microservice from scratch? Well, if you find yourself completely clueless, think of what you would do if you had been given this problem and asked to uh, implement a solution on a single server. So just completely ignore scale for a moment, or for some minutes, and assume that you were given the APIs as a lead code problem. When I say APIs, I mean the functional requirements that you were given. Like the client will submit a query, get back a list of relevant document links. That API can be thought of as defining the function prototypes, the input parameters to your function and the outputs expected by the function, and think of it as a lead code problem and ask yourself, how would I solve it if this was a lead code problem? And uh, good systems design questions will have a problem solving component. And so, as you know from your coding interview prep, if you're given a random lead code problem, it could be fairly hard for you to, you would need some time to a lot of time potentially to solve that problem. So the probability of flunking even a systems design interview is highest if you don't know the underlying problem solving piece or the underlying business logic, as they call it in systems design. And by the way, ignoring scale is not just something you're doing to make life easier for you. It's also the way in which we build systems in the real world. We don't start building them from massive scale from the beginning, because that can be disastrous. You may not even have the money to buy that many machines. When you start, you don't exactly know what you're going to build, what is going to get traction. So it's important in the initial stages to do rapid experimentation to understand who is going to use your product, how will they use it. And then when you find that people are using your products, your service so much that you're unable to handle the traffic, it's actually a sign of success, because that is, you're getting traction. And that is the point when you seek VC funding uh, and you spend money to start scaling your system. So think of how Google itself scaled. Nobody, built a massive search system from the get-go. They went step by step. So going back, this is what we agreed is our primary functional requirement. This is what our queries look like. And for now, let's assume we have a small scale system, just the plays of Shakespeare, which you can assume are given to you in the form of 37 files lying on your server somewhere. So how would you solve this problem? Um, so again, we don't have time to go through this in detail. This typically takes almost 7 or 8 hours, which I'm going to try to compress down in an hour and a half. But uh, the naive solution you could think of is to do a grep. Whenever a user query comes in, just take that query and do a grep on each of those 37 files. Maybe you have a simple script that will parse each file and check whether each play of Shakespeare satisfies that Boolean condition. If it does, you add it to a like a result list, and then you send it back to the user. The problem is that this is too slow. As we start increasing the size of your corpus, so the word corpus typically means a body of documents. In our case, we said it's just 37 plays of Shakespeare, but at Google scale, it would be hundreds of billions of documents. It's going to be too slow to take each query and then wade through the entire corpus each time. So we have to do something, we have to speed this up. And in algorithms and data structures, the way you speed up when you have a brute force solution is you use one of the problem solving strategies: design, decrease and conquer, divide and conquer, transform and conquer. These are the three broad strategies. So here we'll try transform and conquer. Transform and conquer means that you take your input and you, in our case, the input is this corpus of documents, and you represent the input in a different way, so that when queries come in, whatever that data structure you are transforming that input into, that data structure can handle those queries more efficiently. And so uh, given that we want to track which documents satisfy the Boolean query, or which documents contain the terms in the query, we can think of building something that looks like an adjacency matrix. If you're familiar with graphs, where you see that you're interested in relationships, you want to find out which words appear in what documents. If you had a data structure which can represent that, then you could rely on that data structure to handle your query. So just think of building an adjacency matrix, or as they call it in search engines, a term document incidence matrix, where for each term in your corpus, you record which documents or which place that term appears in. And recall, if you're familiar with adjacency matrices and graphs, you would recall that the entries in the matrix are just a 0 or a 1, depending on whether this vertex has a direct edge to this vertex or not. So in our case, we'll just call it a term document incidence matrix, because on along the rows here, we have words or terms, and along the columns here, we have the documents. Okay, in a graph problem, typically you have the same kind of entity that is connected to other entities of the same kind. Here we have terms on one side, documents on the other. And so we have a term document incidence matrix. Now, you can see that if you look at each term, this bit vector tells you which place the term appeared in. And so if you want to find out which place Caesar appeared in, you just return the bit vector, or rather you return the place for which the value is a 1 in the bit vector for Caesar. If you had a more complex Boolean query like Brutus and Caesar, for example, you could take the bit vector for Brutus and it with the bit vector for Caesar, and then in the resulting uh, bit vector, you check which entries are a 1. And whichever entries are a 1, those are the corresponding plays which satisfy your query. So whether it's an AND query or a NOT query or even a complex query like this, where you have three terms, Brutus and Caesar and not Calpurnia, you just have to work with three bit vectors instead of two and do combination of these AND, OR, and NOT operations. And when you do that, Brutus and Caesar and not Calpurnia would just mean you take the bit vector for Calpurnia and you take the complement. And then in the resulting bit vector, when you see a ones, that means the first play and the fourth play of Shakespeare satisfies that Boolean query. And these are the two plays, for example, which contain the words, both the words Brutus and Caesar. But of course, I can't show you that Calpurnia isn't mentioned in the play because you'd have to read the whole play for that. So this is one way to, or I would say a relatively simple way to do transform and conquer. Now, the next thing you want to do is ask yourself whether this is the best possible data structure. And the answer is no. I don't have time to go through the calculations here, but when you actually work with real corp- corpora and look at what terms appear in them. For example, if you had a million documents, news articles, for example, from New York Times or whatever, and uh, each article might be 1,000 words long. When you actually build out the term document incidence matrix, you would find that across the corpus there might be 500,000 unique words, and there might be a million documents. So your matrix would be 500,000 times a million in size. But the main problem there is that because each of the news articles contains only 1,000 words, it just means that only 1,000 of the entries in that column can be a one. That means only 1,000 out of those 500,000 terms in your overall vocabulary can have a one there, and that means this matrix is going to be a highly sparse matrix. And when you have a sparse matrix, it's not a good idea to use an adjacency matrix kind of representation. Just like in graphs, we would move to an adjacency list. We do something similar instead of, because most of the entries are going to be zero, at least 99.8% of them will be a zero. Why don't we just record which entries are a one, right? So that's, or using the terminology of graphs, why don't we move to adjacency lists? If you're not familiar with graphs, that's okay. Uh, but basically we have a more efficient way to represent our, our matrix, where for each term we are no longer storing an entire bit vector for a million documents. We just store the document names or IDs which contain that word, and that's going to be a relatively small number of documents. So Caesar here appears in document 1, document 2, 4, 5, 6, 132, and so on. So obviously we've gone beyond the 37 plays of Shakespeare here, but these are just some arbitrary values. So the assumption is that each document is assigned a unique doc ID, and uh, we have a list of doc IDs for each term, and this is analogous to an adjacency list. So if I want to find out which documents contain the word Caesar, I just have some kind of data structure here which will give me instant access to this list of doc IDs. And you can imagine what this data structure should be. Because I want instant access, this is going to be some kind of dictionary data structure which will allow me to search. Given a term, it will allow me to search for the adjacency list for that term very quickly. And so I might implement it as a hash table or as a balanced tree of some kind. But in search engines, these lists are not called adjacency lists, of course. They're called postings lists, and they're essentially a list of doc IDs which contain that term. So if we have this kind of data structure built where we have a hash table here representing the dictionary, and the postings lists could be represented as static or dynamic arrays, it's generally a bad idea to use a fixed size array for it, because some of these lists will be really long, some of them will be short. So we might have something like array lists, if you want to think in terms of data structures. Some of them will be short, some of them will be long. And so when a query comes in, a query like Brutus and Caesar, what you do is you look up the dictionary and retrieve the postings list for Brutus almost instantly, retrieve the postings list for Caesar almost instantly, and then you're taking the intersection, right? You're not taking the bitwise AND. You want to find out which document IDs appear in both of the lists. Those are the documents which contain both of the terms. And without going into details, this is very similar to how we do merge and merge sort, and we just follow a two-pointer pass pattern to walk through these two lists using two pointers in a way that collectively both pointers are seeing the numbers in increasing order. So one thing you might notice is that these numbers are sorted. That's not a coincidence. You have to have the doc IDs in sorted order so that you can take the intersection efficiently. And that's the reason why we build these postings lists in sorted order. Okay, so uh, the two-pointer pass would just take time proportional to the sum of the lengths of the two lists, and it's absolutely crucial for the postings list to be sorted in increasing order of doc IDs. So we could, and I'll leave it to you to think about how you would handle or queries and not queries, and extrapolate from there to more complex Boolean queries. But for now, this is the simple solution we want to work with. And once we have this data structure built, clearly any query can be satisfied from there. But the question is, how do we build this data structure in the first place? How do we build this inverted index in the first place? This data structure, this combination of dictionary with postings lists, this is called an inverted index. And any search engine for whatever system you want to build will need an inverted index. The name inverted is just a historical legacy. The first indexes that were built were in the context of databases. So these indexes are different, a little different from that. So we call them as inverted indexes. Now, how do we build that inverted index? Once we build it, it's going to be static. It's not going to change for our purposes. But building the index is uh, what we want to imagine doing. Now, suppose we have a set of documents that you have crawled. Now, these might be the 37 plays of Shakespeare already given to you, or in actual search engines, these might be um, documents that your crawler has crawled, and you will need to extract the text out of those documents, and that itself could be a very non-trivial task. Building a crawler is a non-trivial task. Extracting the text from a given crawl document is also a non-trivial task, given that the documents come in all kinds of formats and languages. But assume that you have some way to do that and extract the text out of it. Now, once you do that, what we want to insert in our inverted index are uh, terms, right? Individual terms here, individual words here. And so we need to take the text of any individual play of Shakespeare and tokenize it. That means break it apart into its individual words, remove white spaces, punctuations, and so on. And so we will need something to tokenize the text. And once the text is tokenized, uh, we don't just insert it into the dictionary. We could insert it into the dictionary directly, but if you think about uh, getting back relevant documents for the user, we might need to modify or normalize the text. So what you see here is capitalization is removed, capital F becomes small f, and plural becomes singular. Right? Just two simple examples of normalization we are doing, so that the terms that we end up with are in singular form, they're all in lowercase, and those are the terms that we insert into our dictionary. Why do we do this? Because if the query if I'm searching for the Roman Empire, a document containing the word Romans in the plural should also be returned to me. So that will happen only if Romans and Roman get treated in the same way. So all variations of the same word should be treated in the same way. And so we want to reduce them to the same normal form. And once we do that, we insert those normalized words, or we build this inverted index out of those normalized words. So that's what the normalization is done by a linguistic pre-processing module. It's this, both of these are typically part of natural language processing courses, but the indexing part is what we are concerned with here. How would we build this index? So if you assume that these documents are being parsed one at a time and being broken apart one at a time, you have a bunch of normalized terms that you're seeing. Let's say you see the first play of Shakespeare. You see that the word Roman appears in the first play. Well, you could start this postings list for Roman having the document ID 1. Then you do this for all the words in the first document, and then you move to the second play of Shakespeare. And let's say in the second play you find the word friend, you find the word Roman again, so you add an extra entry to the growing postings list for Roman. You start a postings list for friend. And so if you build out the postings list in this way, where each document you parse gets automatically the next higher unique ID, imagine incrementing the doc IDs by 1, and uh, taking the words of each document and appending the doc IDs to the postings list of their corresponding words, you would automatically end up with an inverted index structure that is sorted in order of increasing doc IDs. And that is what we will assume, that we have an indexer which can build this inverted index quite quickly, and then once it's built, we just keep using it for serving the search queries.